Hello everyone, my name is Jakub Bokshansky, and together with Anna Mihoc, we will be presenting our work on advancing real-time path tracing with Neural Radiance Cache, or NRC for short. In this talk, we will be covering several topics. First, I will introduce the Neural Radiance Cache technique and its productization in the RTX GI 2.0 SDK. I will also cover one of the APIs that we provide, the core API, and in the second part of the talk, Anna will cover the second API, known as the Diffuse GI API. So let's start by looking at what NRC is. NRC is a new method for caching radiance based on neural networks. It was described in the SIGGRAPH paper originating at NVIDIA Research, titled Real-Time Neural Radiance Caching for Path Tracing. This neural network is trained using path trace data to predict radiance at any point in the scene. So instead of tracing a ray or a path to get incident radiance at a given point, we can simply query the radiance cache to obtain an accurate estimate of that radiance. In a path tracer, we can use this to terminate paths early and query the cache instead of tracing the full path. This way, we will improve both the quality and the speed of path tracing applications. Now let's take a closer look at how it works. In order to use NRC, the application needs a path tracer. But don't worry if you don't have one. We have an API with the built-in path tracer for such applications. The main idea behind NRC is to run a path tracer and collect path and radiance training data for the neural cache. We also modify the path tracer to terminate about 96% of the paths early, typically after about 2 or 3 bounces, and query the cache at their endpoints instead. The remaining 4% of paths are traced to their full length to provide the sufficient amount of training data for NRC to learn from. This approach has many advantages. We are tracing shorter paths, so the path tracer is faster, and we also get less noise thanks to the predicted radiance coming from the cache. This approach needs very few parameters and is independent of the implementation of materials, lights, etc. Therefore, it is easy to integrate into existing applications. And finally, the cache is trained at runtime, so it supports dynamic scenes out of the box. This diagram shows an example of the 3 paths in the path tracer. The 2 on the top are terminated early, after just a few bounces into the cache. The path on the bottom is traced to the full length and provides the training data as indicated by the blue arrows. Let's now quickly discuss how the early path termination works. We recommend the method based on tracking a ray cone, approximating the ray, which spreads along the path depending on the type of surface being hit. Diffuse surfaces cause the cone to grow much faster than smooth specular surfaces. Once the size of the ray cone reaches a predefined threshold, which is controllable by the user, the path will be terminated. In this way, the user can control the length of the path and the trade-off between bias and noise. Another important thing to mention about NRC is how it achieves temporal stability. The video on the left shows the NRC result using weights as trained, without any filtering. We can notice significant temporal flicker in this video. Let's watch it one more time. To solve this, we apply a low-pass filter over network weights in temporal domain, simply by applying the exponential moving average to those weights. The video on the right shows NRC using weights filtered this way, and we can notice significantly better temporal stability. Let's watch this video one more time. Note that the strength of this low-pass filter is controllable by the user to achieve a desired trade-off between temporal stability and temporal lag. NRC is especially great for indirect illumination. The benefit of using it is much less noise produced by the path tracer. We also don't need to trace paths to their full length, making them faster, as there will be less texture loads, shading operations, and so on. The image on the right shows visualization of the cache at primary hits. This is not the intended use case, because it reveals imperfections in the radiance approximation, but it also shows how good the approximation actually is. We can see that even the shadow boundaries and the specular highlights are relatively well preserved. Let's take a look at some comparison images. On the left, we have a basic path tracer producing a very noisy image. In the middle, we have added screen space restir, which improves direct lighting on primary hits, but doesn't solve the noise in indirect lighting. On the right, we have added NRC on top of that, and we get a great improvement for indirect illumination as well.